very special. Is as titled Canadian Duet on Black Hole Hawking Evaporation. Is very special because we have the two speakers in the same day. I hope this the a little bit tough for you, but I hope you cannot realize the time passing. Okay, I'm pretty sure both of the talks pretty excellent, also excited. So the two speakers, okay, one the Donald Page, Professor Donald Page from the University of Alberta, and the other Professor William Onlu from University of the British Columbia. Okay, we'll talk about there's something about the black hole information and the Hawking radiation. Okay, actually we have their very close friend here. Okay, Professor Kishin Chen. Okay, we'll introduce more detail about them. Okay.
Perhaps you also want to announce that on the poster, the ordering was opposite to what we have agreed with the speakers. So the one standing there, or sitting, is actually Professor Arun, not Page. Okay, and Professor Page is here, so he will go second. And so the two speakers, in other occasions, I would say, do not really need much introduction. They are well-known figures in black hole physics. Each has their name in the register in this physics. Professor Unru was connected with the what's called the Unru temperature, and I hope he will say more about that later. His name is I already know that at no time. Is originally a German word, perhaps by missing an E at the end. But this in German means unrest, like vacuum fluctuation. So his ancestors already knew that he would have done something about vacuum fluctuations. Now, Professor Don Page has himself made a name in this field, and there's something called Page time. Now, this name is also interesting on the page. Now, so I hope that you also hear more about the Page time, and so it's really a great honor to have two of them in the same room here in Taipei, and they are here also to attend this second LeCosPA symposium, which is going on for this whole week. For that, we feel extremely blessed and honored. So without further ado, let's welcome Professor Unru, who goes first.
Thank you very much. Can you hear me in the back? Good. It's definitely an honor to be here. I had never been to Taiwan before in my life until about 5 years ago. And since then, this is my fourth visit, I believe, here since that time. So it's becoming almost like home. And I'm glad to be here. What I want to talk to you about is black holes, but in particular as an example of the way in which in physics one can perhaps use analogies, use analogs in order to use one system to understand another. I teach a course in the physics of music at University of British Columbia to students who are not physics students, they're not even science students. And I always start off the class with a joke. How is a steamship like an elephant? Now, of course, one of the problems today is the students stare at me and say, what's a steamship? Anyway.
What's an elephant?
Well, I hope they know that one. Anyway, so I'm getting no answers. They both carry trunks. the elephant. The long nose is called a trunk. And on the steamship, you carry all your clothes in this big box, which was called a trunk or a steamer trunk. Anyway, I get about as much laughs in my course as I did here. But anyway, the reason I do that, that's just sort of a pun, a joke with a pun on it. But in a sense, all of physics is a joke, is a pun just like that, because one constantly finds that the physics in one area turns out to be just exactly the same as the physics in a totally different area. One of the things that we're going to talk about today is fluid dynamics. You know, the stuff that happens in your bathtub as you pull out the drain and let the water go out, versus black holes. They don't seem like they have anything to do with each other. But I hope by the time the talk is over, you will see that they're, in some ways, really the same thing. And in particular, one of the things that we discovered, that Hawking discovered back in the 1970s, was that black holes are not black. They create particles constantly. Particles with a temperature roughly proportional to 1 over the mass of the black hole. Can one try and understand that by looking at other systems? Now, arguments from analogy are very ancient. Aristotle already talked about them. I'm sure there were Chinese philosophers that talked about them, but I don't know them. And one of the questions always is, how far is an argument from analogy a valid argument? If A looks like B in some respects, in how far can you use properties of A to decide about properties of B? It's always got trouble because analogies always have places where they differ. Analogies are never perfect. So A and B will look like each other in some areas and won't look like each other in other areas. And one has to try and disentangle those. One has to try and understand how far one can use A to understand B. But what happens if the mathematics of the two is the same? Does that drive the analogy even more strongly? And how far can one use one system to claim to understand the other system? I'll leave that as a question for you to ask throughout this talk. In 1974, Stephen Hawking came up with the ideas that black holes are not black objects. He was trying to do some quantum field calculations around a black hole. It was becoming very popular in those days to try and do quantum mechanics in gravity. John Wheeler was pushing it. A number of his students looked at questions like that. Hawking went and started doing this calculation and didn't expect the answer that he got. Namely, that instead of simply having a few particles being created when the black hole was forming, because of all the time dependence during the formation of the black hole, that's what everybody expected. Instead, what he found was that there was a constant stream of particles coming out of the black hole, more or less forever. Now, on that last formula, you notice that the temperature is inversely proportional to the mass. The mass of the black hole, of course, from E equals mc squared, is the energy of the black hole. So the temperature is related to the energy. From the standard formula, TdS equals dE, that one gets from thermodynamics, one can integrate that and one finds that there's an entropy for a black hole. The idea that black holes might have an entropy had already been suspected by Jacob Bekenstein. He ran into immense problems, however, The results he got were really nonsensical, because in order to make sense of them, the black hole needed to have a temperature, and they didn't have temperatures. Except suddenly when Hawking did his calculation, black holes seem to have a temperature. That also means it has an entropy, proportional to the surface area of the black hole. 2m is the radius of the black hole. 4 pi r squared is the area of the black hole. And if you take 1/4 of that area, you get the entropy. Of course, there's some units that aren't in here. I always work in units in which G equals h bar equals C equals 1. I have a trouble sometimes when I'm talking, giving lectures, I will point at the screen.
That's an analog.
Yes, doesn't work very well. At least not for the audience, maybe for me. There's a G's, H bars, and C's that I have to put in here. I'm assuming those are all equal to 1. So the mass in this case is measured in units of the so-called Planck mass, which is about 10 to the minus 5 grams. So for the sun, this is of the order of 10 to the 38th. So the entropy is a very large entropy. I'm not going to talk about that entropy. I'm going to be spending all my time talking about the temperature, because that's the actual calculation that we can make. And part of the problem is that if you look at Hawking's calculation, it really makes no physical sense. It's perfectly mathematically correct, but when you look at the physics, you say, wait a minute, that assumption just doesn't seem to make sense. Why? What is the assumption? So let's look at to see how Hawking did his calculation. He said, let's take, we have a field, like the electromagnetic field, or in his case, he used the scalar field because the equations are easier. It works for all of them. And let's say that we've got a certain frequency coming out of the black hole. We ask ourselves, where did that come from? Well, you can use the equations of motion to go backwards into the past. And you find that this must have come from closer to the black hole. You keep going into the past, it has to have come from closer and closer to the black hole. It can't have come from inside the black hole. By the way, this green line is supposed to be the matter that collapses to form the black hole. This black line is the so-called horizon. These are the last light rays that don't get out. In other words, if you think about a sphere of light, as though this was a little flash bulb, the light spreads out from that, then all the light rays get focused parallel to each other, and this size, this area of this horizon never increases. That's the horizon. But that means that anything inside going out has to go faster than light. This is light trying to get out as fast as it can, and it's not getting anywhere. Like the Red Queen in Alice in Wonderland. If you're inside, to go out you would have to go faster than light, but nothing can go faster than light. So, this field can't have come from inside. All you can do is you can propagate it back, and it must have been closer and closer to the horizon. If you go later, it goes down in here and gets closer and closer and closer and closer to the horizon, before finally you get back to the point at which the horizon forms, and then it can escape out to infinity. That squeezing is exponential. The time scale of that squeezing is the time scale of light crossing the black hole, which for a solar mass black hole is about 10 to the minus 5 seconds. So every 10 to the minus 5 seconds, you get a factor of E closer to the black hole. One very rapidly, if one goes late, like 1 second, one gets squeezed a lot. So let's take this time to be 1 second after a solar mass black hole forms. The frequency here is, let's say, about the crossing time, a few kilohertz. What must the frequency be here in this initial state which causes that? Well, it's a few kilohertz times this exponential. Since we're going back, t is negative. So after 1 second, that's roughly e to the minus 10 to the fifth. E to the minus 10 to the fifth is a small number. Or the frequency is, I guess, e to the plus 10 to the fifth. E to the plus 10 to the fifth is a very large number. In fact, they don't even have to tell you what units to use. Because any units you use, it's still e to the 10 to the fifth. If I talk about ages of the universe, or I talk about Planck times, which are 10 to the minus 44 seconds, that just makes a tiny little difference to that e to the 10 to that 10 to the fifth. Do I believe that I understand the physics of this quantum field at frequencies of e to the 10 to the fifth? If I multiply that by h bar in order to get an energy, that's e to the 10 to the fifth times the mass of the whole universe. Do I believe the equations, once the frequencies are such that the energy of a single quantum would be e to the 10 to the fifth times the mass of the whole universe? Well, no, come on. Something's got to break down. That was Hawking's calculation. Well, one has two attitudes. One can say, well, all nonsense. On the other hand, it really seems to work. By means to work, we'll see soon. If we could do experiments, of course, those experiments would therefore be definitive. They would tell us whether we're right or not wrong. The problem is finding black holes is really hard. For a solar mass black hole, this temperature is around around 10 to the minus 6 Kelvin. This is stuck in a universe whose temperature is 3 degrees Kelvin. It's really hard to see something of a temperature of 10 to the minus 6 Kelvin in a background of 3 Kelvin. One would need very small black holes, and very small black holes are really hard to find. Back when I was a graduate student, a postdoc in London with Roger Penrose, Dennis Schauma at the University of Oxford asked me to come and give a colloquium on black holes to the University of Oxford. And I was scratching my head trying to decide how could I explain what black holes are. In the early 1970s, black holes did not populate all popular literature like they do now. People really hadn't heard about them. So I came up with an analogy, and the analogy is the following. Let's pretend that we have a world of fish. These are very intelligent fish. They're physicist fish. These little protuberances here are not fins, they're ears. Because these fish experience the world only via the sense of sound. Now in this world there happens to be a particular virulent waterfall, such that at some point the velocity of the water is equal to the velocity of sound. This is obviously not our world, because in our world you would need to have the water dropping about 10,000 kilometers before the velocity of the water equals the velocity of sound, but that's just a minor engineering difficulty. This could be Terry Pratchett's Discworld. I don't know if any of you have ever read Terry Pratchett. Anybody? He's a very good English author, just recently died, who has a world in which magic rules, and the world lives on the back of an elephant which lives on the back, which stands on the back of a big tortoise, which slowly swims through space. Anyway, in this world, there's a big ocean, and that ocean at the edge of the world falls off of the world in a waterfall, and so perhaps this is that waterfall. When Terry Pratchett was asked, how is it the water falls off? How does it get back so the world doesn't get all drained? He just said, it is arranged. Anyway, so let's imagine we've got this world, and this professor here has his graduate student to investigate this very strange phenomenon. And this graduate student gets a little too close to the edge here. Now, if that graduate student tries to talk to his professor here, the sound waves that he emits will gradually go outwards like this. They will, of course, travel a little bit more slowly upstream than downstream because the flow of the water is sweeping them over the waterfall. But what happens if that fish yells just at that point where he's passing that point, where he's passing that line where the velocity of the water equals the velocity of sound? Well, then the poor sound waves, which are trying to travel outwards, are swept back over the waterfall at exactly the same rate, and they never get anywhere. They just sit there. Sound waves traveling in other directions are, of course, swept over the waterfall. Furthermore, for sound that's emitted just outside, it takes a long time for it to get out. The closer it is to that surface, the longer it takes to get out. So therefore, the wavelengths of the sound would get stretched longer and longer. The sound would be base shifted, just like light is redshifted near a black hole. If this graduate student yelled for help just as he was passing there, the professor would just hear something like, help! Because the sound would get base shifted, and the final P, which was emitted after he passed this, would never get out. Of course, whether or not the professor would even pay any attention, even if he had heard it, is an open question. This is just what black holes are like. Light rays, instead of sound waves, light rays behave this way in the vicinity of a black hole. Something falling into a black hole, the light is redshifted as it's coming, the light is redshifted that gets out to infinity. And in fact, it becomes infinitely redshifted just as you go through that surface. There's nothing really unusual about that surface. In other words, this fish wouldn't notice that he passed that surface. The importance of that surface is the relationship between it and sound traveling out to infinity. No particularly strange physics would happen just at that surface. Anyway, I gave the colloquium. I used this as my little analogy. About 8 years later, I was teaching a course in fluid mechanics at the University of British Columbia. And one day, while I was preparing my lectures, my mind started wandering. I thought about this little analogy, and I thought I should do some calculations. I've learned a bit of fluid mechanics now that I've taught it. That's how professors learn stuff, by teaching it to students. I've learned a little bit of fluid mechanics, so I calculated the propagation of sound inside a flowing fluid like this. And lo and behold, if you assume you have an irrotational flow, what you find from the equations of motion, this is Bernoulli's equation, this is the conservation of mass for the fluid. If I eliminate rho from this equation and I do small fluctuations, I get an equation that looks like this. But this equation turns out to be exactly the same as the equation for for
The black
a
hole.
scalar field in a metric, where the metric has components given like this. In other words, the mathematics of sound waves in this flowing fluid is exactly the same as the mathematics of scalar fields, like around a black hole, that Hawking used in order to calculate his thermal radiation. So one should be able to do exactly the same as Hawking did for this system. And there's a horizon. The horizon occurs in these situations. We won't talk about that. Anyway, what one discovers is that this system also emits thermal radiation by exactly the same arguments as Hawking gave, with a temperature now not proportional to the inverse mass, but proportional to the spatial derivative of the velocity of sound squared minus the velocity of the fluid squared, evaluated at the point where those two guys are equal to each other. So the temperature is again determined by the geometry of this background fluid flow, just as it is for black holes. And this derivation suffers from exactly the same problems that Hawking's derivation did, namely that e to the 10 to the 5th. This also says that the thermal radiation coming out, if you go backwards in time, hugs that horizon, that sonic horizon, and exponentially blue shifts. And finally, when you have to wait until finally the black hole, or this dumb hole as I called it, dumb here does not mean stupid. Dumb is from the original meaning of the term, deaf and dumb, which means not being able to speak. So these are holes which are not able to speak. Of course, in the case of sound waves, we understand that that hydrodynamic equation isn't the last word. We have the atomic theory of matter. The fluid is made out of atoms. You can't have wavelengths of e to the minus 10 to the 5th. That's much, much smaller than the distance between atoms. And it doesn't make sense to talk about sound waves whose wavelength is much less than the distance between atoms. So there's an automatic cutoff in this theory. Does that mean that in this theory that thermal temperature is killed off? Or can one get a clue as to what's happening in the black hole case from this system? Well, I had a lot of trouble trying to figure out. I sort of saw myself having to solve the Schrödinger equation for 10 to the 23rd water atoms in a fluid. It's completely hopeless. And it was Ted Jacobson a few years later. I fortunately gave a colloquium, not a colloquium, a seminar on this at the University of Texas, where Jacobson was a student. And this stuck in his mind for about 10 years. And he realized that the important thing about the atomic nature was it altered the dispersion relationship, the relationship between frequency and wavelength of the sound waves, such that it's not simply a linear function. F is this relation between frequency and sound waves. That's not a simple linear one with the velocity of sound in front, but is a much more complicated function in general if you have the atomic nature of matter. Here are some examples of dispersion relationships. This is the kind of dispersion relationship that you get in water or liquid helium. In liquid helium, it actually goes up, comes back down, and then goes up again. In a Bose-Einstein condensate, you get a dispersion relationship that looks like this. And the frequencies that are allowed are the places where this line, whose slope is the velocity of the fluid, intersects this dispersion relationship. Well, I wrote this up in a Fizerev letter, and I called the paper Experimental Black Hole Evaporation.